Hi, I'm Rob, this is Chris, Matt and Ryan, and we're working with PTE Hydraulics designing a rotary actuator testing rig. So who is PTE Hydraulics? They are a Brisbane-based company who is one of the largest specialised manufacturers of hydraulic cylinders in Australia. Recently, they have expanded production to include rotary actuators, and they're looking for a method to accurately test their products. So what is a helical rotary actuator? Essentially, it is a powered hinge. Rotary actuators convert the linear motion of a hydraulic piston through a set of carefully designed helical splines and gears, which in turn produces a high torque rotation. This allows for operation in a large range of applications where lifting, lowering, tilting, slewing and rotation are required. So what is a testing rig? Testing rigs vary greatly depending on their intended use. Any form of test that acquires data from a device or system has used a form of testing rig. The current facility at PTE Hydraulics headquarters is essentially a pendulum, where an actuator has an attached arm and mass which is left to run for multiple hours. This, however, could only test the fatigue resistance of internal components, seals and bearings of the device. The testing rig was unable to record any numerical data that could be used for product specifications.
PTE custom design and manufacture their actuators. They currently only have theoretical standards and no practical boundaries at which their systems can operate within. This is where our team comes in. Our main goal is to have a test rig which provides a maximum loading torque in both static and cyclic loading to a rotary hydraulic actuator. PTE needs a test rig so they can provide these values as standards to their customers. The information recorded from the test rig will provide safe operating boundaries for these actuators. When testing under cyclic loading, the actuator must not receive large shocks. As the actuator reaches its limits of rotation and changes direction, it will experience a large shock impact force. Appropriate systems will need to be implemented to reduce this impact. The test rig will not be designed to reach the actuator's braking limits, as these systems are expensive to manufacture. PTE have provided us with specifications of a higher-end actuator that they aim to test. This 470 kilogram actuator has a design pressure of 3000 psi, a dynamic torque of 31.5 kilonewton meters, and a holding torque of 60 kilonewton meters. The testing rig must be designed to complete 180 degrees of rotation. As testing multiple sized actuators is required, it must be adaptable with various mounting sizes and methods. Due to the risks involved with the large torques and high pressures, the testing rig will need to also be safely enclosed to avoid causing damage to surrounding structures or people in the event of failure.
Our team has created an initial design concept that will provide a solution to the loading challenges and supply the necessary data to PTE. The design consists of a mounting for various sized rotary actuators, a torque arm and a linear actuator. All of these components will be attached to a rigid framework suitable for the loading conditions and workshop environment. The linear actuator will provide counter-loading to the rotary actuator through the torque arm. The hydraulics in both actuators will be controlled through an automated programmable logic controller, or PLC for short. The linear actuator can be controlled via PLC to provide static loading or long duration cyclic loading for the model being tested. The use of PLC means directional changes at the end of each cycle can be smoothly transitioned to avoid shock loading, which was a significant contributor into the decommissioning of the last test rig. PTE has access to a wide range of linear actuators, so sourcing one will be easy and cost efficient. A system of sensors will be implemented to provide feedback to the hydraulic control system and record loading data for the post-test analysis. One of the main design challenges regarding the linear actuator concept is achieving the full 180 degrees of rotation. Incorporation of the gearbox into the system is being investigated. This will reduce the angle of rotation of the torque arm while also providing a more even forcing distribution across the range of motion.
While the linear actuator system is a great solution to the design requirements, there have been other design concepts which are yet to be completely ruled out as standalone design options or even partial incorporations into the primary concept. These include a mass torque arm system, a mass pulley system, and an opposing rotary actuator rig. The proposal from PTE defined criteria for loading conditions, but we got the impression that another issue they were having was that they had no real-world simulation. So why not try to replicate practical conditions during the test phase? The incorporation of a sealed chamber to introduce particulate flow and create elevated temperatures while the rotary actuator is being loaded will mean that PTE can be sure of the integrity of their products before they leave the floor. This environmental chamber is an innovative design option that we are excited to investigate throughout the conclusion of the design phase.
I will be refining our current loading scenario concept to overcome the challenges associated with the test rig.
I intend to calculate and design the structure to ensure the framework will be able to withstand the actuator's reaction forces.
My role is to investigate the control systems and sensors to be implemented in this design, to provide automated operation and quantitative results.
I aim to further investigate the environmental chamber to create a real-world simulation for the operating actuators. So our plan for this project is to present a complete design including cost analysis and material sourcing to proceed to the manufacturing process.